So we are discussing computer organization subject, and we are in module 3 or unit 3, and we have started discussing cache memory, and we'll just make use of the Jamboard which I initiated. These are a few of the keywords which I put on the Jamboard. Starting with cache, because this is the topic we are discussing, cache memory. Now, what we can say related to cache memory? When we discussed cache memory, we said that, or when we discussed the memory hierarchy, we said that cache memory is the next nearest to the CPU after the registers. So it's a high-speed memory, fast memory, costly memory, nearer to the CPU in the memory hierarchy. Nearer to the CPU in the memory hierarchy. What else we spoke about cache memory? We spoke about cache memory that frequently required instructions and data. Frequently required instructions and data, if they are kept in the cache memory, then the memory access time will be improved. The memory access time will be improved. Thereby, the execution of the program also improves. Thereby, the execution of the program also improves. What it indicates, so whenever a program is to be executed or a task is to be done, a CPU will not refer the main memory for whatever data or whatever instructions, whatever table, whatever array it requires. It will be referring the cache memory. It will be referring the cache memory. If it doesn't get the required data from the cache memory, then the CPU will be accessing the main memory. Then the CPU will be accessing the main memory. That is what basically is the concept. Whatever is available in main memory, let us say main memory, you treat it as a big space. So cache memory will be a very small space as compared to the big space of the main memory. So not the entire content of the main memory will be available always. Only a limited content, need-based content will be available in the cache memory. Need-based content will be available in the cache memory. So now all these advantages, whether it is improved access time, improved execution time, all these advantages of cache memory are exploited because of a property called as locality of reference, which I have recorded here. Just a confirmation to all of you. Am I audible to you? Am I making sense to you? 1 or 2 yes will be okay for me to go ahead. Just say yes if you are listening to me, if you are understanding the things. Yeah, Balram, am I audible to you? Adil, am I audible to you?
Yes,
Yes,
sir.
sir. Yes, sir.
Okay, so I can move ahead. So once you understood the purpose of a cache memory, you should understand that whatever advantages we are getting of the cache memory, we are getting that because of a property called as locality of reference. Because of a property called as locality of reference. What is this property called as locality of reference? So it has the meaning like this. Listen very carefully. Let us say a program is to be executed. For executing that program, CPU has to bring the data as well as the instructions of that program. So the program is sequential in nature, top to bottom, first line, second line, third line, fourth line. But this sequential nature is broken because of subroutines or because of loops. You may be writing while loop or for loop or do while loop or some subroutine or some go-to statement if it is allowed in that programming language. So basically, this is what your program is. So where an analysis of many programs which are executed by the CPU is done, what is found out is in a program, whatever data, whatever table, whatever variable, whatever instruction is fetched from the memory to the CPU, it is fetched from the nearby locations. It is fetched from the nearby memory locations. It is fetched from the nearby memory locations. So this nearby memory locations are referred multiple times. For example, there is a loop of 100, 1 to 100. It means 100 times the same memory location is accessed. If there is a subroutine which is called multiple times, as many times the subroutine is called, those many times the similar memory address is accessed. Let us say there is an array. So array also, suppose array has, let us say, 100 elements. All those 100 elements are in nearby memory locations only, contiguous memory locations. So basically, the references to the memory for accessing data or for accessing some instruction are nearby, similar, repeated. So this property is called as the locality of reference. Hopefully you understood the meaning of locality of reference. Yesterday I gave you the analogy of a ball. Ball. For example, you can take any other analogy. So I can say locality of reference in a classroom. Though we may have forgotten the classroom, but let us say there is a disturbance coming in the class. I usually look at the place from where I feel or there will be trouble every day from some one place. Is it? Or maybe the last 2 benches, maybe the middle 3 benches, like that. So you can treat it as locality of reference for me. My gaze will automatically go to the place where I feel that this is the common place from where I'll get the trouble. So you can take this analogy also to relate with locality of reference. Now, the next word which we need to connect with is hit and miss. Now, to understand hit and miss, we need to understand the purpose of a cache memory. So tell me, one of you tell me, so what is there in the cache memory? Anybody can tell? Snigdha, can you tell what is there in the cache memory? Vinay, what is the purpose of a cache memory? What is there in the cache memory? Okay, anybody in the class? Okay. Somebody, you can put in the chat window also if you're not comfortable talking. What is the purpose of a cache memory? What is kept in the cache memory? Because we want to understand this term hit and miss. So for that, we need to remember what is there in the cache or what is the purpose of a cache.
Sir, the main purpose of the cache is to keep the most frequently accessed instructions and data in a fast memory.
Excellent. Very good. So we know that cache memory is a memory, but it is a small memory as compared to the main memory. CPU will not go to the main memory, but CPU will go to the cache memory and check whatever data it wants or whatever instruction it wants, it is there or not. Okay. If it is there, it will be fetching that. If the CPU is successful in getting the data from the cache, then that is called as a hit. But let us say the CPU tries to access some data and it is not available in the cache. It means it's a miss. So hit and miss. Whatever data I want is there in the cache? Yes. If the answer is yes, hit. If the data I want is not there in the cache, then it is a miss. So suppose the data is not there in the cache, what will be done is then the main memory will be accessed. And once in the main memory you get the data, the copy of that data will be kept in the cache. The copy of that data will be kept in the cache. And not all the data from the main memory will be there in cache. Only limited data will be there in the cache, is it not? So it means you will be frequently replacing the content of the cache. Okay, so you may apply some algorithm like a round robin algorithm, first in first out kind of thing. So so some old one from the cache will go and some new one from the cache will come. But cache also has cache is never empty. So cache is never empty. There will be some data. So you need to check whether the data is valid or not. You need to check whether the data is valid or not. So for validity check also there will be validity bits, zeros and ones. Okay, that also will be referring. So basically what we need to remember is what is a hit and what is a miss. Data is there in the cache, hit. Data is not there in the cache, miss. Now what is a hit ratio? Coming to the next word, hit ratio. So what is a hit ratio? The hit ratio means hits divided by the total references. So hits divided by hits plus miss, you can say. Hits divided by hits plus miss, you can say. Or hits divided by all the total references by the CPU. All the total references by the CPU, hit ratio. Well, what is the purpose of a hit ratio? Hit ratio is a parameter used for cache performance analysis. If the hit ratio is good, cache performance is good. If the hit ratio is bad, cache performance is bad. So the hit ratio is near. Many people researchers who have analyzed the hit ratio, they found out that the hit ratio of 0.9 also is possible. The hit ratio 0.9 also is possible. So it means the property of locality of reference which is exploited by the cache actually is useful. And ultimately this entire cache and locality of reference and hit ratio, all these concepts will be used for this purpose. Improved memory access time and execution time. Improved memory access time and execution time. So what cache consists of? Cache consists of some data from the main memory. Now, this transformation of the data from the main memory to the cache, will be done with the help of a process called as mapping. And there are different types of mappings. For example, you may use associative mapping, or you may use direct mapping, or you may use set associative mapping. Now here we are using a word called as associative. For that you need to remember associative memory concept. What was the associative memory concept? When we were using associative memory, whenever we wanted faster search. And this is a costly memory than the main memory. It means for implementation of cache, we may use that associative memory concept. These are the three techniques of mapping basically. Associative mapping, direct mapping, set associative mapping. If it is associative mapping, you are using the concept of associative memory. And you remember that argument register, key register, matching register, and all that concepts. You remember, because we had discussed associative memory in the previous two classes before. We had discussed that. So now we need to understand this concept of associative mapping, direct mapping, and set associative mapping. So I'll be referring your syllabus textbook of Maurice Mano for the same. But again, we'll make a walkthrough of the cache memory content just to verify whether we have missed something or not. So this is our cache memory. And the first keyword here we are referring is locality of reference. The second keyword we are referring is hit ratio, hit and miss. Then we are saying average memory access time is good. Now coming to mapping, what is the meaning of mapping? We said the transformation of data from main memory to cache memory. The transformation of data from main memory to cache memory, it is called as mapping. Okay. So what are the three types of mapping? Associative mapping, direct mapping, set associative mapping. What is the meaning of associative mapping? It uses associative memory concept. What is associative memory concept? You have to remember our previous discussion. Let me take you through that diagram. This is the block diagram of associative memory, wherein you had argument register, key register, and matching register. This was the example. The key register will be deciding how much part of the search string is to be used for matching, and parallel search will be done. So basically your associative memory will be used, for parallel searching. Okay, faster. With parallel searches, faster search will happen. What is the meaning of parallel search? All the memory words in the memory will be referred at the same time, for matching. This was our associative memory. But where are we? What we are discussing now? Actually, we are discussing cache memory. In cache memory, we are discussing mapping of cache memory. Cache memory mapping, we are saying three types: associative mapping, direct mapping, set associative mapping. You have associative mapping, direct mapping, and set associative mapping. Now, for that, in your textbook, to understand these three concepts, the textbook is saying that you must connect with this diagram. You should be able to understand this diagram. So let us look at this diagram, so that this diagram will be used to make us understand these three concepts called as associative mapping, direct mapping, and set associative mapping. Associative mapping, direct mapping, and set associative mapping. Now, what this diagram is showing me? This diagram is showing me there is a main memory, there is a cache memory, and there is a CPU. And CPU has a direct line with the cache memory, as well as the CPU has a direct line with the main memory. It means CPU can directly access the contents from the cache memory as well as the contents from the main memory. For example, here it has given that the size of this main memory is 32K by 12. 32K by 12. So 32K means what? 32,000 words. 32K means 32,000 words. What is the word size, word length? The size of each word will be 12 bits. So what this 32K by 12 indicates? The size of the main memory is 32K by 12. It means what? This main memory is capable of storing 32,000 words. The size of each word is 12 bits. Now, if you compare this size of the main memory with the cache memory, you can see that cache memory is very, very small as compared to main memory. Here in main memory, how many words are there? 32,000. In cache memory, how many words are there? 512. It means at any time, cache memory is capable of storing 512 words from the main memory. Cache memory is capable of storing 512 words from the main memory. And the word length is same. The size of the word is 12 bits. That's fine. Now, once we understood this diagram, as the book says, using this diagram, hopefully we'll be able to understand associative mapping. For understanding associative mapping, we should remember the concept of associative memory. Okay. So that diagram which I referred. Now, let us directly look at the associative mapping. See here, this is my cache memory. Now, this cache memory consists of what? It has all the data as well as the address. The cache memory has the data as well as the address. Okay. And as it is using associative memory concept, there is an argument register. Is used for what purpose? The argument register is used for searching. For searching what? Whatever data CPU wants. So for that, CPU will be providing the address. You can see here the 15 bits being used by the CPU for addressing. 15 bits being used by the CPU for the addressing. Now, if you look at the cache content, in the cache there are three words. In the cache there are three words. Word number 1, word number 2, word number 3. Okay. So, not only the data as well as the address, it contains both the things. It contains the address as well as the data. It contains address as well as the. Hopefully you are following me. If any doubt is there, you can always ask me. You can stop me also. Now, here the address bits which are 15 bits, they are shown as the 5-digit octal number. And so the data word, 12-bit data word is shown as a 4-digit octal number. We remember that this is our data word size. The size of the word is 12 bits. This 12 bit data is shown as a 4-bit octal number. And this 15-bit address is shown as a 5-bit octal number. This is an argument register. Remember the use of argument register. So CPU will be keeping the address here in the argument register for whatever it want to search. So whatever is to be searched, that address will be kept here. So this address will be compared with the addresses available here in the cache. So if there is a matching, the corresponding data will be given to the CPU. So you have this address and data pair, and you have this argument register and usage of associative mapping in the cache. So one technique, the way mapping is done is associative mapping. And what is mapping? We are transforming data from main memory to cache memory. So hopefully you are able to connect with it. But we also know the limitation of the cache. Cache does not contain all the content of main memory. Some limited content, for example, here 512 words. It means you have to go on removing some content from the cache, adding content in the cache. That you have to go on doing it. So how you are going to do it? Maybe you will be using that round robin, which I told, or the first in first out replacement algorithm. So this was one way of implementation of cache, associative mapping. The second way of implementation of cache is direct mapping. Now, why we are going for direct mapping instead of associative mapping? Or associative mapping memories, we already know that they are costly memories. Because they have to do parallel searches. So instead of associative memory, we'll be going for the conventional random access memories. Okay, and trying to implement direct mapping through random access memory. Same thing will be here. The address bits which are of 15 bits, now that 15 bits are divided into two parts. One part will be of 9 bits, the other part will be of 6 bits. The 9-bit will be the index and the 6-bit will be the tag, and the 6-bit will be the tag. So you can relate this with this written thing here. If in the cache memory there are 2 to the power of k words, okay, and 2 to the power of n words in the main memory. So your memory address, which is n-bit memory address, which is 15 here now, this n-bit memory address is divided into two parts: k bits for the index and n minus k bits for the tags. If you are getting confused with this, just remember that your address, the number of bits for the address are 15 bits. These 15 bits are divided into two parts. One part will be of 9 bits and the other part will be of 6 bits. So this 9-bit will be called as the index and the 6-bit will be called as the tag, and the 6-bit will be called as the tag. Now this is your main memory and this is your cache memory. Remember, here also we had the same thing. This we wanted to understand. Main memory, cache memory, size of the main memory, size of the cache memory. 32,000 words, 512 words. Same thing you can see here. The size of the main memory is 32,000 words. The size of the cache memory is 512 words. The size of the cache memory is 512 words. Now, the address bits are 15 bits. The data bits are 12 bits. That is given. See here, the data bits are 12 bits. The data bits are 12 bits. The address bits are 15 bits. Now this 15 bits are divided into two parts, 9 bits and 6 bits. So the 9 bits of address, that is the index part, 9 bits of address, that is the index part, are used by the cache, while the complete 15 bits of the address, that is both the tag and the index, are used by the main memory, So this is the difference here. You can see here direct memory cache organization. Look at the cache memory content. Cache memory has index and tag, and this is the data. Index plus tag is equal to what? Index plus tag is equal to total address. Index plus tag is equal to total address. So how matching will be done? The matching will be done first with the index. The matching will be done first with the index, then with the tag. The matching will be done first with the index, then with the tag. That's how. Here there is an example being shown here. Let us say the index is 000 and the tag is 00. Let us say the index is 000 and the tag is 00. Our data is 1220. So our data is 1220. There is a matching. No problem. Now let us say the CPU wants to access a word at the address 02000. So you have 02000. You actually want, CPU wants this data, 5670 data. But it is at which location? This is at location 02000. So 4 zeros. Sorry, 3 zeros after 2. These are the 5 bits. Now, what will happen is when the matching is done, you find that there is no such index called as 02. There is no such index called as 02. So when no such index 02 is there, then sorry, just a minute. Let me follow this example. CPU wants which data? Data at the address 0200. What is the index? Index is 00. Okay. Now, then the tags are compared. Okay. The cache tag is 00 and the address tag is 02. So there is no matching. Then the main memory is referred and then the required word is accessed. And that cache word which is there at the index 000, it will be replaced with the new one. So this is your direct mapping example. Mapping example. Now you can also have blocks. This was only referring to one word at one go. One word, one data at one go. But here you can have block of words. For example, 8 words in each block. So there are 64 blocks. Now in such a case, when block is there, you are dividing your address index part into block and word. So block number and word number. Rest of the thing will be same. So this is the second technique. The first technique was associative mapping and the second technique was direct mapping. Coming to the third technique, which is a set associative mapping. Why set associative mapping? Because there is a disadvantage mentioned above related to direct mapping. What is the disadvantage? It may be possible that there may be two words. They may be having the same index, but they are having the different tag values. Okay, in such case, they cannot be at the same place in the memory. So hence, to overcome this, the set associative mapping is used. Let us look at this diagram directly. As you can see in the set associative mapping, you have the index, but at the same index, you have two different tags. So that is the significant difference between the others. So at the same place, you are having two different tags. It means you are having two different data. You are having two different data. So this is what is your three techniques for mapping. These are the three techniques for mapping: associative mapping, direct mapping, and set associative mapping. Now, coming to the next concept, whatever we have discussed till now, that was reading from the cache. Whatever we have discussed till now, that was reading from the cache. But suppose we want to write into the cache. So there are two ways of doing it. One way of writing to the cache is write through method, and the other way of writing to the cache is write back method. You can see in the Jamboard I had written that two keywords. That is the write through and write back. Write through and write back. These are the two techniques of writing to the cache. There are two techniques of writing to the cache. What is the meaning of this? The meaning of write through is simple. Whatever you are writing in the cache, same thing you will be writing in the main memory. Or so at the same go, any updates are also there at the same go, at the both the places it will be occurring. It means main memory is always updated. If you are following me and listening me carefully, then you understood this. Then otherwise, I am sure you have not understood this. Second technique is write back technique. What is the meaning of write back? Any updations are there, they'll be reflected only in the cache memory. They'll be reflected in the cache memory only. They'll not be reflected in the main memory. But at a later stage, slowly, though, that update will be reflected. So these are the two techniques, write through and write back, whenever we are writing the content to the cache. As far as cache initialization is concerned, so as I said early in the class, today's class, that there may be some data available in the cache. So after initialization, that data may be invalid data, data may be valid data. So that we can check with the help of a valid bit being set. So initially the valid bits are set to 0. So whenever we are making an entry into the data cache, for that word, as it is a valid word, we are making the valid bit to be 1. So this way we are ensuring by comparing it with the tag, matching happens and valid data is there. So this is what is today's discussion. We covered cache memory. We try to understand various keywords from the cache memory. What are the keywords? Locality of reference is one word. The other one is hit ratio, the meaning of hit and miss. The three types of mapping, that is associative mapping, direct mapping, and the set associative mapping. So hopefully you understood today's concept. So now what I'm going to do is I'm going to take the attendance. So only